Thank you for introduction, and welcome to Kyoto. So today I'd like to talk about ill-posedness. Later I'll explain what is ill-posedness. Ill-posedness of the third-order nonlinear Schrödinger equation with Raman scattering term. So this is a joint work Nobu Kishimoto, Limus. So the third-order nonlinear Schrödinger equation is like this. So here is a third-order dispersion, and here is the second-order dispersion. And this is a standard cubic nonlinearity, and this is a derivative of cubic nonlinearity. So this term is called Raman scattering term. So through the Raman scattering, the system in question exchanges energy with the external environment and with initial condition, and we consider the problem under a periodic boundary condition. So it's torus or a circle. Here the constant alpha j, gamma j, and capital gamma are real constant with both of alpha 1 and alpha 2 doesn't vanishes, and capital gamma 1 is not equal to 0, of course, because in my talk this term is important. So small I denotes imaginary unit, capital T positive constant, which denotes an existence time of solution. Usually the size of T depends on the initial data. So as I already told you, the last term on the right-hand side of equation 1 represents the effect of Raman scattering. This term. Oh, sorry. In my talk, we always assume that if alpha 1 is not equal to 0, then 2 times alpha 2 over 3 times alpha 1 is not integer. So this is called a non-resonant condition. Later I will explain it in more details. Unknown function u from interval minus tt times t to c denotes slowly varying envelope of electric fields. So this means for some large omega positive, electric field capital E is represented like this. So 1/2 times e2 minus I omega t u plus complex conjugate. So this is usually called slowly varying envelope approximation by physicists. So this figure shows you an image of pulse with slowly varying envelope in photonic crystal fiber. So you represent this envelope, and factor e to minus omega t expresses this rapid oscillation. So for more details of physical background, please see the book by Agrawal, Nonlinear Fiber Optics. So this is a famous book in this optical physics. So now my problem is, this is a mathematical problem, is the Cauchy problem of equation 1 well posed in Sobolev spaces in HS. So what is the well-posedness like? The well-posedness of the Cauchy problem consists of the following 3 notions. First, the existence of solution. So local existence or global existence, it depends on the problem. The second, the uniqueness of solution. third, continuous dependence of solution on initial data. So this is originated by Adamar. So if any one of these three conditions fails, we say the Cauchy problem is ill-posed. For the last 2 decades, the research of nonlinear dispersive equations, such as the Kota-Wegg-Brice equation and nonlinear Schrödinger equations, has made a great progress. There were pioneering work by Burgan, Koenig, Ponce Vega, and Coriander, Kiel, Staffiani, Takaoka, Tao, and others. Especially Jean Burgan had been the driving force behind the development of the research in this field for a long time. So one of fundamental problems in nonlinear PDE is how does nonlinearity in question make sense? So let me show you one example. So consider the Cauchy problem of the Kota-Wegg-Brice equation. KDB equation is like this, and with initial data here. Initial data belongs to the Sobolev space HS. Here, S is larger than or equal to -3/4. So that means this initial data is not function distribution. It is well known, generally, the product of two distributions are not well defined. So however, when we take two solutions of KDB equation, instead of general functions, the product U squared becomes well defined because of a nonlinear smoothing effect. So this is also helpful for the study of ill-posedness issue. Now, I would like to tell you our main theorem on the ill-posedness. The first theorem concerned with non-existence of solution. So we assume the non-resonant condition. So later I'll explain it. And S and S1 satisfy these inequalities. Then there exists initial data in HS, Sobolev space HS, such that for any capital T, the Cauchy problem of equation 1 with initial data equal to U naught has no solution toward positive time, nor solution U towards negative time. So I'd like to mention one remark about this theorem. So the first remark is, instead of T, when we consider equation 1 or R, so it is known that local well-posedness holds in regular Sobolev space. So the solution exists at least small time. This is due to Hayashi and Ozawa and Chihara in 1998. The spectrum of the Laplacian on T is discrete, while it is continuous on R. So the difference between T and R comes from the nature of the spectrum of Laplacian. The second remark is, even if alpha 1 is equal to 0, that means even if the third dispersion term vanishes, the theorem 1 holds. The second theorem is concerned with the breakdown of continuous dependence of solutions on initial data. So again, we assume non-resonant condition. And let S larger than equal to 1, and U star, let U star be solution to equation 1 on time interval 0t for some capital T. Then, for any epsilon positive and for any tau less than capital T, there exists real analytic function phi with its HS norm is less than epsilon, such that either there is no solution U to equation 1 in C0 tau to HS with initial condition U equal to U star 0 plus phi. So phi is perturbation. Or such a solution exists, but this inequality holds. The supremum over T of in 0 tau of HS norm of U of T minus U star of T is larger than epsilon minus 1. So this kind of claim is often called inflation, norm inflation. So I'd like to mention one remark about theorem 2. Theorem 2 implies, the second theorem implies the breakdown of continuous dependence on initial data, as I already told you. The assertion of theorem 2 is weaker than theorem 1 because theorem 1 says no solution. But the former can cover a larger class of initial data than the latter. In that sense, a theorem is better. Now, let me explain an idea of proof for theorems 1 and 2. So let me assume solution U exists in certain function space. Then equation 1 has conservation law of mass. That is, the L2 norm of solution is conserved as long as solution exists. Now, I would like to mention one remark about the conservation laws of equations. The momentum and the energy are not conserved because of the Raman scattering effect. So as I already told you, through the Raman scattering, the system in question exchanges energy with the external environment. So momentum and the energy are not conserved. So this is one of the reasons why the Cauchy problem is ill-posed. So let me first apply the translation and the gauge transformation to equation 1. So new dynamical variable denotes V. And this path represents translation, and this factor represents gauge transformation. Now we work with V. Then original equation 1 can be written as follows. dTd plus IA times dxd. A is defined as gamma over 2 pi times the L2 norm of initial data squared. So now we have the mass conservation. This is equal to the L2 norm of the solution. And here are linear dispersion term. And this deduction of the L2 norm of solutions comes from this factor of the gauge transformation. And this deduction of the L2 norm squared comes from this translation. And this term comes from the Raman scattering term. So now this sum is taken over K1 plus K2 times K2 plus K3 not equal to 0. Of course, if K1 plus K2 equal to 0, this term vanishes, and the sum over K2 plus K3 equal to 0 amounts to amounts to this term, I times A times dxv. In fact, we have another unpleasant term, but this second factor of gauge transformation excludes that unpleasant term. So that disappears. Oh. Now, yes. This is Cauchy-Riemann operator. So the Cauchy-Riemann type elliptic operator, dt plus ia times dx, appears due to the Raman scattering term. So this gives rise to the ill-posedness of the Cauchy problem. However, our equation is of a third order, and the equation includes the nonlinearity. So the ill-posedness is not obvious. So we need to confirm the effect of the Cauchy-Riemann operator is dominant over the nonlinear effect. For that purpose, the nonlinear smoothing effect is useful. So I'd like to make a remark about the elliptic regularity theorem for the Cauchy-Riemann type operator yields no solution U both towards positive and negative time for n capital T. So this is slightly weaker than theorem 1. So let's back to yes, here theorem 1 says no solution U towards positive, nor solution U towards negative. So now I would like to emphasize, so the ill-posedness proved by the elliptic regularity usually say this type of results. That is, the initial datum is interior point of time interval. So in this respect, our theorem 1 is stronger than usual elliptic ill-posedness result. So for the proof of theorems 1 and 2, we need to use the dispersive nature of equation. So this implies a smoothing type effect. At this point, we need to assume non-resonance condition. Now we work with interaction representation. That is W, new dynamical variable W is defined as, so this is the inverse of linear evolution operator and times V. Apply the Fourier transform in X variable to equation 3. So a little bit complicated, but okay. Important matter is we have three kinds of terms on the right hand side. So this is a resonant term. Resonant means, later I'll explain what is resonant. So frequency is the same, just K, only K appears. Here K1, K2 plus K3 equal to K, because this is the Fourier transform of cubic term, so the convolution appears. So this is the convolution, just convolution. This is also just convolution. But these two terms are called non-resonant because here oscillation factor, what is capital phi? Here capital phi is defined as this function. This is okay. This part is linear dispersion term, right? The Fourier transform linear dispersion term. This function phi represents the interaction of four waves. Interaction of four waves. More precisely, interaction of three waves produces one new wave. So this is called four-wave mixing. And so under non-resonant condition, function capital phi is equal to 0 if and only if K1 plus K2 times K2 plus K3 equal to 0. Because under the non-resonant condition, this factor is not 0. So by this observation, if function phi does not vanish, then modulus of function phi is similar to modulus of K1 plus K2 times K2 plus K3 times modulus of K3 plus K1. So this relation implies we can have we can gain extra derivative. So that leads to the smoothing effect. So let me first consider the resonant term, the resonance case. So usually this case is most difficult. But if we consider the regular solution, it doesn't matter. So in this case, we consider just the solution more regular than energy space or in energy space. So the resonant part does not cause a problem. It's easy. So if S larger than or equal to 1, then modulus of K times, I forgot to say the definition of capital F. Yes, so F1, F2, and F3 denote, yes, let me denote F1 hat, let me denote this factor, this term by F1 hat, this summation by F2 hat, and this summation by F3 hat. So the first, the resonant term, less than some constant time, modulus of k to minus 1, k2s times modulus of w hat cubed. So this is almost obvious. Here we can gain one derivative. So this is a smoothing action. As I already told you, so if S is larger than y equal to 1, this is the energy space. The resonance term can be easily controlled. But if we consider the solution in a bigger class of the energy space, this is the worst term, worst case. So let me go to non-resonant case. The time integration of, okay, so yes. Here is a factor, oscillation factor, e to it phi. And here is also e to it phi. The time integration of F2 hat and F3 hat leads to the smoothing type effect thanks to the oscillation factor of EIT phi. So you can imagine a Cauchy-Riemann theorem. Therefore, there exists initial data U naught in HS such that if T positive, the modulus of E to a TK times U naught hat. So this is a homogeneous part of the equation. This tends to infinity, and so this part is the so-called Duhamel term, non-homogeneous, inhomogeneous term over the homogeneous part combined to 0 as k to infinity. Respectively T negative, respectively as k minus infinity. So this relation implies homogeneous linear part is dominant over the nonlinear Duhamel term. Then we have theorems 1 and 2. Now I would like to say a few words about physical literature related to the Ill-posedness. So I think this is interesting. So there are several papers, physical papers, about a kind of instability of the system. For example, El Quintaro, Genti, Betzel, and Dudley, they study the limitations of the linear Raman gain approximation. The linear Raman approximation is just our Raman scattering term. And Tura and Biancarana studied unphysical metastability of the fundamental Raman solitons. So some physicists say the linear Raman gain approximation, that which is just our Raman scattering term, is apt to lead to inaccuracy of numerical computations and unphysical phenomena. So I personally contacted Biancarana according to suggestions of Japanese physicists. So in his email, he says, so it is apt to lead to instability, but this approach is universally, this approach means equation 1 is universally used among physicists. So it's just strange, looks strange. So the mathematical notion of ill-posedness is interpreted as the instability of a physical system at hand. But it is not very clear whether this instability accounts for some physical phenomena or it's implied just a limitation of the model. But I should say one more word. So a large number of numerical simulations for the Cauchy problem, equations 1 and 2, have been made, though it is ill-posed in Sobolev spaces. But the important thing is, in those numerical computations, such analytic functions as Gaussian and super-Gaussian pulses are chosen as initial data. So it is natural to expect that the Cauchy problem should be solvable in the analytic function space. So this is the Cauchy-Kowalski theorem. Indeed, we can prove the result on the unique solvability in the analytic function space. That is the second part. So let me briefly explain the solvability in analytic function spaces. The norm of space A is defined small L1, norm of e to r times k times f hat for positive r. And space A is defined f in L2 such that this norm is finite. So let me remark about this space. Functions in this space A are real analytic and have analytic extension on the strip imaginary of Z less than R. The function space A was already used by Ukai for the Boltzmann equation, or by Kato and Masuda for a class of nonlinear evolution equations such as nonlinear Schrödinger equation, and by Fourier-Tillman for the incompressible Navier-Stokes equation. The third theorem is just the abstract Cauchy-Kowalski type theorem. So let alpha j be two real numbers. So we allowed alpha j to be 0. Because dispersivity has nothing to do with this theorem. And let R positive. For any initial data U naught in A of R, there exists capital T positive such that the Cauchy problem 1 and 2 has a unique solution. U in C minus TT to A. Moreover, the existence time T is bounded below by a minimum of Y and M R times AR norm of U naught minus square inverse. This is not surprising. And where the implicit constant does not depend on R and initial data U naught, implicit constant appear here. So I'd like to mention a remark about theorem 3. Theorem 3 is a kind of the so-called abstract Cauchy-Kowalski type theorem. So we do not have to assume this non-resonant condition. Even when alpha 1 and alpha 2 are equal to 0, theorem 3 holds. The interesting open problem is, it is not known if the solution given by theorem 3 exists globally in time. Some numerical simulations suggest that when the initial datum is Gaussian or super Gaussian, the solution may exist globally in time, or at least for a long period of time. Or what if the initial datum is a hyperbolic second pulse? This is the exact soliton of cubic NLS. This function is also used as initial data. But the Gaussian is analytic on the whole space, but hyperbolic second is analytic on the strip, just strip. So maybe there would be some difference. And the third result is the ill-posedness in the Gebre class. So in the linear PD theories, the Gebre class plays an important role concerning the well-posedness and ill-posedness. So this Gebre class often give a sharp boundary between the ill-posedness and well-posedness. So it is natural to ask if the Cauchy problem is well-posed. Our Cauchy problem is well-posed in the Gebre class or not. Now, let me quickly define the Gebre class. So let's sigma larger than or equal to 1, S is non-negative, and A is positive. Space J sigma SA is defined F in C infinity, and the Fourier coefficient of K decays like modulus of K to minus S e to minus A modulus of K to 1 over sigma. If sigma equal to 1, this space is an analytic function space. The normal space G sigma SA is defined this quantity. Here, angles K, angles parenthesis K denotes max of 1 and modulus of K. Now, the Gebre class of order sigma is defined as all the union over A positive of G sigma 0A. So I'd like to a little bit about the topology of Gebre class. So the space, this is a simple space. The space G sigma SA is a Banach space. But G sigma is not the Banach space. The Gebre space G sigma is equipped with the finest locally convex topology that makes the embedding G sigma 0A into Z sigma continuous for all A positive. But we have general theory for locally convex topology. I don't want go into details about the topology. So this is my last theorem. So let's sigma larger than 1. For any initial data U naught, this sigma not in intersection, this space. There exists no capital T positive such that the Cauchy problem has a solution. So this is just a consequence of the following, a kind of smoothing effect. So let U belongs to C0TT to D sigma be a solution to equation 1 for some capital T positive. Then this solution must belong to this space. So this implies solution U must be a little bit regular, because it's in the intersection over all A prime. Okay. Thank you for your attention.